In this video, we're going to take a look at how to compute potential energy surface scans with Sci4. So in this notebook, we will take a look at the rotational barrier of hydrogen peroxide. Let me start by importing Sci4. To simplify things here, I have created a function called geometry that takes in as an argument phi, the dihedral angle, and it generates a Sci4 molecule object, calling the Sci4 geometry function. In this function, I have a block of text here, but I'm using a formatted string. So I can specify a Z matrix that corresponds to this labeling of the atoms that I've used up here. I've fixed the oxygen-oxygen bond length, and oxygen-hydrogen bond length, and the oxygen-oxygen-hydrogen bond angle to the values that correspond to the optimal values for this molecule. The dihedral angle here, it's labeled as D, is passed in through this function and inserted into the text directly when I provide a value. So this function allows me to quickly generate a Z matrix for a given dihedral angle. So let me run the cell. That's going to run and define the function. Okay, now we can test this function. And here I'm going to use the ForteCubeView module. This is a Python module that you can easily install. There's a link here on this notebook, and that will direct you to this GitHub page that describes how to install ForteCubeView. Now, if you have Py3.js, you can easily install ForteCubeView by typing pip install ForteCubeView. Otherwise, you first want to set up Py3.js and tell your Jupyter notebook or Jupyter Lab how to find this plugin. Let's go back to the notebook. So if I now run this cell, I'm going to first import ForteCubeView. Then I'm going to call the geometry function, which just allows me to visualize a molecule. So here I can pass the molecule argument. It can be a Sci4 molecule object. And I'm going to generate a geometry with a 60-degree dihedral angle. So it is. Here's our molecule. You can see the 60-degree dihedral angle. If we change, say, this to 180, so you can see there's the image gets updated only once I hover it on with the mouse. There you can see there's a 180-degree dihedral angle. Okay, now that I've verified that this function works, we're going to start to do our first scan. So in the first scan, I'm going to do what is called an unrelaxed scan. So I'm going to change the dihedral angle in the range 0 to 180 degrees. But I'm not going to optimize the geometry. I'm just going to define a geometry with the function geometry that I've defined above. And that means I'm not relaxing the bond lengths and bond angles. So here I set up a list of angles that ranges from 0 to 180, stepping in 5 degrees at a time. And I've initialized an empty list that will contain the unrelaxed energies. I set up a loop over all the variables, and inside this loop I generate a molecule with a given dihedral angle. I pass this to psi and compute its energy. And here I'm just using Archifock theory, using a split valence basis set. If you want to repeat this exercise on your own, you can modify all the choices that I've decided to make here. For example, you can use a density functional method. You can increase the size of the basis set. You can make the grid a little bit finer. It's up to you. I capture the energy here once I call sci4.energy, and then I store it into my list. And I'm calling the sci4.core.clean function just to clean up any temporary files. This is a good practice if you're going to repeat several calculations. Okay, let me run this cell. and it will take a second to complete. Okay, my calculation is now done. But before looking at the results, I'm going to do my second calculation, in which I do a relaxed scan. Now, if we want to do a relaxed scan, in this case, we want to initialize a molecule with a given dihedral angle. But we have to constrain that dihedral angle. Otherwise, Psi4 will optimize all the geometric variables. So here I'm setting up this option. This is an option for the geometry optimizer in Psi, where I specify a fixed dihedral. I have to pass it a string which contains the list of atoms involved in that dihedral, and then I specify the angle, which I pipe in through a formatted string. So now, when I perform the optimization inside this loop, I first of all get a molecule that has a given dihedral angle, and I have asked Psi4 to not modify that angle. Let me run this, and this will take a couple minutes. Okay, the calculation is now done, and if you scroll down, you can see all the prints from Psi4. Now, let's take a look quickly at the data. So I'm going to just print a list energy relaxed, and it shows all the values. Now, this next step is going to be optional. And the idea is to save our data to disk. Now, I'm doing this because if you use Jupyter, sometime the kernel might die if you do something wrong, or it could be that your terminal dies or your connection dies. So it's important to be able to recover the data and avoid repeating calculations that we've done before. So what I'm going to do now is to use JSON, which is a text-based format for storing data. And JSON is a format that's very similar to a Python dictionary. So here I'm importing the JSON module. I define a dictionary of data where I store both the unrelaxed and relaxed energy lists. And then I open a file called results.json. And in this file, I dump all my JSON data. As I said, this is optional, but I really recommend it. Now, if we go to my folder, you can see that this file has been created. And if we look into it, there is our data. You can see the unrelaxed energies and the relaxed energies. Now, I could stop here, for example, and then pick this problem back up at a later time. I just have to load this data with JSON. It's pretty easy to do. Now, the next thing I'm going to do is make a plot of the energy scan. I'm going to use matplotlib because it's convenient. There are several tweaks that I do here, and I'll walk you through those. So first of all, import pyplot and matplotlib in general. I found this line to be very convenient, especially if you have a high resolution monitor. This enables 2 times resolution images to be plotted in Jupyter. Next, I'm going to find the minimum energy of the relaxed scan, and I'm going to use that as a 0. I'm going to shift all the energy with respect to the 0, and I'm going to transform the energies in kilocalories per mole. So this is what I do in the next 2 lines. I'm just using list comprehensions, and I shift the energy and multiply times the conversion factor from atomic units to kilocalories per mole. Then I set up my figure. I like to customize the size of the fonts, the size of the figure. This is the width and the height in inches. And later on, I might want to edit this figure in Illustrator. So I add this extra line, which sets the fonts to be a true type. So this means I can edit the text in it through Illustrator. I would say this is definitely an optional thing for you to do. You don't have to do it if you're just going to take a look at the figure as it is. Here are a couple extra tweaks. These eliminate some lines in the plot so that it doesn't look like a box. I define my labels, the X and Y labels. Then I plot the data and pass the unrelaxed and relaxed energies. And at the end, I do a couple commands. I add a legend, and I use this tight layout command, which cleans out the proportion of the image. And last, I'm going to save this image to a file called plot.pdf. So if I run all this block, this generates this figure where I get both the unrelaxed and relaxed energy curves. As you can see, the minimum is around 100 degrees. There's a low barrier transition state and a higher barrier transition state. And you can see that, especially for the high barrier transition state, there's a sizable difference between the unrelaxed and relaxed energies. So you can see that this is the same figure that I've used in my notes on transition state search. So that's all for this video. I encourage you to explore this feature of Psi and learn how to impose constraints on bond angles and bond lengths. Thank you for watching this video, and I hope that you found it useful.